Hello, chemistry class. So it's Mr. F, your chemistry teacher, and I am just welcoming you into a fun and exciting world of chemistry. That's right, we are here live in the chemistry classroom. I'm happy to have you here. Let's take a walk up to the front and we can get started with today's lesson. So, welcome back. Great to have you here. Today, what we're going to be talking about is essentially a brief history of the atom, of matter, where it came from, the key players, okay? Democritus, or as I like to call him, Democ, he's a close personal friend of mine. Aristotle, what they thought matter was, what they thought everything out there was composed of, how it differed depending on who was theorizing, who supported them. Maybe did chemistry get was chemistry in the back seat for X amount of years because we believed one over the other? Were either individuals supported? How can we prove this? That's what we're going to answer, those questions and a whole bunch more today in Fabianski's Chemistry Corner. I swear, I got a new name for this every time we do it. I look forward to you guys taking a look at these notes, and I hope you enjoy it. Hey everybody, welcome to the PowerPoint. It is your teacher, Mr. F. Today we're going to be talking about the atom, and we're going to look at the particle theory of matter. Just kind of get our feet wet a little bit, take a little walk around, see what we can figure out. I did promise you some interesting stories about my man Democritus, and another gentleman named Aristotle. You're probably familiar with Aristotle, but you probably never really heard of Democritus before. Well, we're going to introduce those two gentlemen to you and kind of figure out what exactly is going on. So, taking a look at this, I guess I got to move me around a little bit. Hey, I'm down here now. Democritus, he came about in 460 BC, and he thought matter was this stuff that makes up everything in the world, right? We're made of matter, the desks are made of matter, the board behind me is made of matter, the air is matter. And matter, all of that stuff was made up, matter makes all of that stuff up. That's what he called it. It's like, hey, what makes up this calculator? It's got to be matter, right? So that's what he named it. And then he went one step further and he said, hey, matter is made up of these things called atoms, right? They're invisible particles, but they make up matter. And what's really weird with this is that, to think about it, invisible things make up something that is visible, something that we could see, something that we could touch. So it was so out in left field, it was so revolutionary during this time that he said something invisible makes up something that we could touch, okay? It's there. So he was the first thinker to argue for a void. And a void. What does that mean, a void? Well, again, taking a look at our calculator, he said that there was more space in this calculator than there was matter, which is weird, right? There was so much space in this calculator that, there was so much space, more space than there were atoms. So kind of a revolutionary thinker at the time, okay? However, the problem became that others just didn't agree. And if you don't want to take my word for it, take Mr. Carl Sagan's word for it. Carl?
For Democritus, all of life was to be enjoyed and understood. In fact, for him, understanding and enjoyment were pretty much the same thing. He said, a life without festivity is a long road without an inn. Democritus may have come from Abdera, but he was no dummy. Democritus understood that the complex forms, changes, and motions of the material world all derive from the interaction of very simple moving parts. He called these parts atoms. All material objects are collections of atoms, intricately assembled, even we. When I cut this apple, the knife must be passing through empty spaces between the atoms, Democritus argued. If there were no such empty spaces, no void, then the knife would encounter some impenetrable atom, and the apple wouldn't be cut. Let's compare the cross-sections of the two pieces. Are the exposed areas exactly equal? No, said Democritus. The curvature of the apple forces this slice to be slightly shorter than the rest of the apple. If they were equally tall, then we'd have a cylinder and not an apple. No matter how sharp the knife, these two pieces have unequal cross-sections. But why? Because on the scale of the very small, matter exhibits some irreducible roughness. And this fine scale of roughness Democritus of Abdera identified with the world of the atoms. His arguments are not those we use today, but they're elegant and subtle and derived from everyday experience. And his conclusions were fundamentally right.
Wow. That was excellent. Thank you, Mr. Carl Sagan. So continuing on, let's talk a little bit about our friend, now someone who battled Democritus. His name was Aristotle. And Aristotle came about in 384 BC. Now, completely contradictory to Democritus, Aristotle said, no, matter is not particulate. There aren't these atoms. No, no, no. Matter is instead continuous, right? It's there's no stopping. There's no void. Okay? There's no space. Democritus, there's space. There's a void. Aristotle, no space, no void, continuous. But who's right? Aristotle also said something else. He said, matter was not made up of these atoms. Instead, matter was made up of the 5 elements. Fire, earth, air, water, and this thing we call ether. And ether is the stuff up there. It's the gods. It's space, right? When you pass, according to Aristotle, your soul, your body would go into the ether. So he believed that those 5 elements, not the elements that we're familiar with on the periodic table, but those 5 elements made up everything. Now here's the downside. One gentleman we know to be correct and one we know to be, well, not. But neither had proof, and that's a problem. See, neither could provide evidence to support their claims. So for that reason, and back in these times, science really wasn't that, people really didn't pay too much attention to it. They didn't really like it. They thought it was like sorcery. So these two gentlemen really their beliefs weren't backed. Okay? And that's a problem. And if anything, Aristotle's beliefs were backed a little bit more than our friend Democritus. And we know Democritus, he was the man. Democ, he was the man. He had it right. But no one really backed him. So alchemy, both a philosophy and a practice, with the aim of achieving ultimate wisdom as well as immortality. It was like sorcery. It was, dare I say, witchcraft, but it wasn't really witchcraft. It was more like sorcery, right? Alchemists would do these experiments. They would try and turn water into wine or silver or lead into gold, okay? They would do these crazy experiments, have these explosions, these puffs of smoke. I mean, for this reason, we lost a lot of alchemists. They would inhale poisonous chemicals. They would taste stuff you do not do in the lab right now. They would be blinded by explosions that would go off in their face. Okay? Their goal was to try and make these substances that had these unusual properties, these new substances. They were doing chemistry before they knew it was chemistry. Something to take away from this, Aristotle's beliefs, they were more along the lines of alchemy. Okay? The 5 elements. Now, people tended to gravitate more towards alchemy, more towards Aristotle, than they did towards Democritus. For this reason, chemistry, it was kind of put on the back burner for nearly 2,000 years. So sadly, think how much further we would have been if we all followed Democ and Democritus, and we would have been 2,000 years in the advance. Would have been amazing. So continuing on, I'm going to do a couple demos to kind of prove to you that Democritus was correct. So if you guys want to join me, we're going to go over to the lab area. I will see you guys in just a second.
Whoa. How'd you guys get here quicker than I did? All right, anyway, let's get started with some of these experiments to try and prove to you that Democritus is right. First thing, since we are in the chemistry lab, we need to put on our safety goggles. All right, so I'm not going to put these on until after because there's probably a wicked echo, but I want to show you exactly what we're doing first. I'll put these aside for now. So here we have a bin of water. I also have a little portable Bunsen burner and an empty can. There's nothing in there right now, but I am going to put in a little bit of water, just a little bit. I'm going to put on my safety shield here, and I'm going to light this burner. Now what I'm going to do is heat the water in the can. Now as this is heating, we're seeing some stuff that's starting to happen. You guys are going to have to take my word for it, but the water's starting to boil inside. Okay, we're starting to get some steam that's starting to evacuate out of the can. So what's going on here? What's in that can right now? There's air, just like there's air out here. And the air out here is pushing in on that can, and the air inside of there is pushing back out. So right now that can is in perfect balance. It's not getting pushed in too far, and it's not getting pushed out too hard. I can see the steam starting to come out, at least I can. So now, since that steam is starting to evacuate, it's pushing all the air out. So what's filling the inside right now? Well, steam. But watch what happens when we take that can and turn it over in the water and we block the air from going back in. Ready? 3, 2, 1. All right. And you see what happens there? The can, well, was it crushed or was it sucked in? It was actually crushed. See, as that steam was coming out, it pushed all the air out. Now you have air on the outside pushing against water vapor on the inside. Everything's in balance. Everything's happy. When we turn the can over and block the mouth and block air from getting in, there's no more heat source, so the water vapor turns back into water. Air can't get in to fill the space, and we're left with so much pressure outside pushing in and no counter pressure pushing back out that the outside.
All right, everybody, just to recap. With regard to the can collapse demo, when the can was heated, the water turned into steam. The air inside became hot, causing the molecules to move further and further apart. The expanding air was forced out, filled by the steam from the water vapor. Less air molecules meant less air pressure in the can. Now, what happens then? Well, when we take the can and we flip it, we're stopping the air from going back into the can. And now this means there's more air pressure, more air particles, more air molecules on the outside pushing in, and that crushes the can.
Democritus was right. We just didn't know it at the time. Now in our next demo, what I have here is just water and a 25 milliliter graduated cylinder. I'm going to fill that graduated cylinder up to 25 milliliters with just deionized DI water. Nothing special, no tricks here, nothing. That ding means there definitely isn't any tricks. I'm not going to cut the camera, I'm not going to edit this because I want you guys to believe me when I do this. So this is 25 milliliters right now, okay? You're just going to have to trust me. I could bring it up to you guys and show you, but it is exactly at 25 milliliters. I apologize. You can see the last line there is 25. I have another 25 milliliter graduated cylinder, and I have ethyl alcohol. So what I'm going to do is I'm going to fill that graduated cylinder with 25 milliliters as well. Go very easy here. And this one is a little bit more, just a smidgen. If you watch some of my other videos, yes, smidgen is a scientific word. Perfect. 25 milliliters. Now, everyone knows if I take 25 milliliters of a liquid and 25 milliliters of a liquid and add them together, that I will get 50 milliliters. 25 plus 25 is 50. There's no way around it. So let's take this clean, empty, 50 ml graduated cylinder, and let's add in our 25 mils of alcohol. Make sure we're getting that all in there. No drops left behind. It's empty. And we're just going to take a look at this. I know I'm doing this really inaccurate by not putting it down on a flat surface, but it is at 25 mils. Now I'm going to take my 25 mils of water and I'm going to pour it in there, and we will see that it should add up to 50 mils. 25 plus 25 is 50, empty. And now, make sure it's all good. And oh my goodness, it's not 50. It is not 50. 25 plus 25 is not 50. In fact, if I were to put this down and measure it, it is actually at 47. We're missing 3 milliliters of a liquid. 47 milliliters. 25 plus 25 is 47. Why? There was no cut to this. There was no editing. I could bring you guys down here and show you. In fact, I think I will. I will bring you down here and show you. This is flat on the ground, and you could see there that there's the 50 line, and that reading is at 47. So what's going on there? Well, hate to break it to you, but Democritus was right again. There's a void. There's space. So we had ethyl alcohol and we had water. The ethyl alcohol molecules are large, very large compared to the water molecules. So think about if you and your friends are standing with your arms out and you're touching fingertip to fingertip. So you're standing here and then there's another person standing there, fingertip to fingertip. There's space, there's void in between you. That void, you can actually take another person and put them right in there. When you're standing like this, you're the ethyl alcohol. When you're in between the space, you're the water. The water actually fills the space in between the ethyl alcohol molecules. The void. Democritus was right again. Okay? You can't make this up. This is live. No, it's not live. It's on YouTube. It's recorded. But regardless, it's live right now. Democritus was right.
All right, everybody, just to recap with what you just observed, 25 plus 25 does not equal 50. The particles or molecules of one substance will fill the space between the particles or molecules of the other substance. Okay, this is supporting the fact that we do have a void. There's a space, okay, in matter. Just like Mr. Sagan said, Mr. Carl Sagan said, when you cut that apple, it's cutting through the void. So I know it sounds weird, but there's more space in this calculator than there is actual matter. There's more space in you and I than there is actual matter. It's crazy to think about, but hopefully you enjoy this and you look forward to this crazy journey about chemistry that we'll learn this year. So everyone, have a wonderful day, and I can't wait to see you guys in class. Take care, everyone. Bye-bye.